Welcome to NPTEL course Transfer Phenomena in Bioprocess Engineering, week 3. So, this class we will discuss about the fluid flow dynamics in the flat plate. So, why you want to study this process here? It's very important it's a very important significant play a role in bioprocess engineering, because most of the operations are carried out the fluid phase. So, definitely we need more idea about the fluid phase here. So, then of course, next one is directly influence the mass transfer, heat transfer, then mixing efficiency. Sometimes it will definitely affect the nutrients to the cells and the growth and productivity. So, then whenever the fluid undergoes the continuous deformation, when the contact is solid support, there is a shear force, definitely get disturbance. So, we definitely need thorough studies about the shear force and the shear stress and how to minimize the on sensitive biology system. So, these are the fluid flow dynamics varies with respect to various dimensions. So, like a flat plate for membrane and biofilm, then circular tube, pipeline, the transport nutrient and gas, then circular tube channels, heat jacket, the sphere is the immobilized beds. The fluid flow dynamics in plot plate, you just see here this one, the water is flow from here to here, this side, and the angle is a beta. Okay, if it vertical, then it's like automatically get 0, but here the beta. The thickness of the film thickness, this one is a delta, and then the length of the total length is L. The W is the width of the flat plate length here. So, whenever you want to do, we need assumptions. Without assumption, we cannot solve that one. So, velocity is constant throughout the place. Velocity is constant. First, you have to assume this one. Then the density of fluid, rho of fluid is also constant. Of course, sometimes the velocity vary, rho also vary, but assumption to make this one, the velocity is constant, then the density of fluid also constant. Then the flow is a laminar. The flow is a laminar, and then steady state condition. There is a steady state, unsteady state is there. If time dependent, that is steady state. Time dependent is unsteady state. Time independent, that is a steady state. Of course, it should apply for Newton's law of viscosity, because Newton's law of viscosity always the tau shear stress, whether non-Newtonian fluids or Newtonian fluids, that definitely we need that one. Then disturbance, so the film thickness is very less compared to that L and W. So, here the Vz is a function of x, y, z. So, that means that all three direction the velocity is here. For small flow rates, so we can write for V of z equal to only for Vz function of x. Same way for P equal to the pressure equal to P of x, because of the hydrostatic effect in the only x direction. So, that is only we are giving here P equal to P of x. You just see here, you assume this is okay, small x, and then this x plus delta x, the thickness is here delta x, the same plate, and we are just giving this one z equal to 0. At z equal to 0, what is this one? Same way for z equal to L, the distance is here L. So, the angle is here the beta angle here. So, y equal to 0 to W, y equal to W, that the width of that one, the width is here, y equal to 0 to W. Okay. Then L is the length of that one. So, here of course, we know that one, now we always call the tau xz, that the shear stress tau of xz, there is a velocity Vx, Vy. Then as per Newton's law of viscosity, the tau of xz, we can write off this one minus of mu dv z by dx. So, Newton's law of viscosity here. So, then the volume of this one, the control volume length is L, then W is the thickness of delta x here. So, how you write here for rate of momentum for only for viscous transport, the rate of momentum flux here x equal to L into W tau of tau x is at x. is a shear stress, normally is unit is Newton per meter square, and then here is area meter square. So, same way for rate of momentum flux at x plus delta x, this is a x this point, then what is the x plus delta x here. So, this is the one point. Then another one is for what is the gravity force acting on the fluid z direction. So, there is L W delta x rho g cos theta, that is a gravity force, that also we have to add here. The first one we discussed viscous transport, then other one is for convective transport. The convective transport rate of momentum flux at z equal to 0, we always write W delta x of, here the Vz will come, Vz of this one, at z equal to L, and then the same way there is a velocity here, that is called convective. Whenever viscous, the viscous always the shear, the Newton's first law will come always. Newton's law of viscosity will come here picture. So, after rearranging this one LW of this one, the first one is viscous this one, then due to gravity we are writing here. So, then divided by the throughout the equation divided by LW delta x, if you divide it by this one, then we will get delta x the first one, then other one is for rho g cos theta equal to 0. So, you want to solve, then rearrange this one, then this will come this side, rearrange this one. So, there is a here sign conversion will be there. So, you apply here limits of delta x tends to 0, then we will get this one d of d by z equal to rho g cos theta. So, the tau x z we can write tau z equal to minus of mu dv z by dx, is a Newton's law of viscosity. So, once this done Newton's law of viscosity, then you differentiate this one, then we can write d square v z by dx square equal to minus of rho g cos theta, this one, after rearrangement this one. So, first this one dv z by dx, the dv z by dx equal to minus rho g cos theta, you integrate this equation, basically you have to integrate both sides, then we will get here instead of this one dv z by dx, we will get a dv z by dx equal to rho g cos theta this one, then plus c1, some constant will be there, say integration, okay, integration. So, we again integrate one more time the same equation, integrate one more time. So, then this will be a v z equal to rho g cos theta x square by 2 plus c1 plus c2, one more the constant derivative will be here after the second integration, So, now you have to apply the boundary condition, there is a different boundary condition is there, like complex boundary condition or mixed boundary condition or very simple boundary condition is there. But here we are only discussing very simple problems. So, the simple boundary condition you give for x equal to 0, when x equal to 0, the tau of x is equal to 0. So, that means that the dv z by dx equal to 0, because the tau again we can write minus of mu dv z by dx. So, automatically this will be a 0, x equal to 0, so we can write this one. So, if we use this equation for dv z by dx here the equation, because x equal to 0, this part is 0, this also 0, then from here we will get c1 equal to 0. Okay. So, then another boundary condition, the boundary condition 2 you have to apply here. The boundary condition 2, there is a x equal to delta, that is v z equal to 0. When x equal to delta, the thickness is delta, then v z equal to 0. So, this equation you have to use, but already c1 is 0, the c1 is 0. So, we have only c2 is there, the v z also 0. So, then if you solve it, then c2 equal to rho g this one. So, of course, you know the constant c1 and c2, you substitute the above equation, we will get the beautiful expression of this one. So, after rearranging this equation, v z equal to rho g cos theta delta square this one. So, now we use a two boundary condition, one is x equal to delta and v z 0, other one is x equal to 0, then dv z by dx equal to 0. So, two boundary condition we use, based on situation, based on the problems, we have to change the boundary condition. So, here at x equal to delta, then v z equal to 0, then at x equal to 0, what is the value of? At x equal to 0, if you substitute here, then we will get a v z of rho g cos theta delta square by 2 mu, that we called as the b max. V max, the maximum velocity. So, we can find from here maximum velocity. So far we discussed maximum velocity, then what is the average velocity? Average velocity, of course, you have to integrate the V system, V is the dx by and then dx. So, the thickness is 0 to delta, the limit is 0 to delta because the thickness is 0 to delta. You here automatically this just for assumption, okay, you will get both will get cancelled, then only we get the velocity. Okay. So, V z equal to here, we know already what is the V z equation, take that equation. So, only this part we integrated here, we got 2 by 3 delta here, then the V z equal to rho g cos beta delta square by 3 mu. So, it is a 2 by 3rd of, because V max already we know V max. So, 2 by 3rd of V max equal to the average velocity. Sometimes they may ask, okay, what is then the pipe flow, what is the average velocity, what is the maximum velocity. So, we need thorough idea about that one. Then the fluid flow dynamics in flat plate, volumetric flow rate you have to see. So, here volumetric flow rate Q equal to the unit is meter cube per second. So, what we can do here, you take meter per second, that is the velocity, then multiply with the area meter square. So, we will get a volumetric flow rate meter cube per second, that is there. So, velocity we used Vz, but the area we used here dx dy. Since we want to thorough problem that overall what is the volumetric flow rate, then we have to integrate the whole system 0 to W, then 0 to delta. So, once you integrate this equation, of course, Vz we know already, from there you just substitute Vz here, then integrate this one. Anyway, this is W will come here, the first one is W, then the dy here. Okay. So, after rearranging this one, then we will get Q of this one, Q equal to W of rho g cos beta delta square by this one. So, this volumetric flow rate we can use the Q value, it is very easy volumetric flow rate. So, the unit is here meter cube per second volumetric flow rate. Even if you use all this one, then finally we should get the unit should be a whatever we have mentioned here. So, this is the overall volumetric flow rate here. The same problem how to calculate mass flow rate. So, the mass flow rate here, normally mass flow rate unit is kg per second, but of course, already we know. So, normally we write mass flow rate W sometime m. So, here Q into rho. So, what we this unit is kg per second we mentioned, of course, Q volumetric flow rate you know meter cube per second, then the density units you know kg per meter cube. So, both will get cancelled, then you will get a kg per second, that is a mass flow rate. So, the mass flow rate W we can write Q into density, multiplication of that one. The same you know already Q value, you multiply the density, then we will get a beautiful expression of mass flow rate. So, sometimes they may ask what is the film thickness with based on the mass flow rate. So, you take delta equal to this equation. Same if from volumetric flow rate how to calculate, same delta you can use from here, this is 3 So, first we discuss maximum velocity, then average, then what is the force per unit area, that is Fz. Okay. So, normally we write tau shear stress equal to F by area, force by area, that always we write. So, the force here tau into area, that is shear stress into area. So, there is a shear stress here and the area is here. You integrate the system because the whole system is 0 to L2, then 0 to W. So, integrate and then again you know what is tau Z, this is a Newton's law, you just use this Newton's law, minus of mu dV Z by dx, but at x equal to delta. So, we integrate this equation, then rearrange, then finally we will get a beautiful expression of the force per this one, the rho g delta cos beta LW. It's just small integration, it's a very simple. Finally, we get this one, force per unit area. So, this equation definitely we need many assumptions such as steady state, then the smooth flat surface, it should be a constant flow rate, density constant, then only we can solve it. So, through experimentally we have observed the Reynolds number we can write Reynolds number equal to you know dV rho by mu. So, there is a V is there, velocity, then density is there, okay, then the thickness delta is there, then mu. So, we can write in terms of Reynolds number for fouling film, we have to write here. If Reynolds number less than 20, but this case is the less than 20 only. So, there is a our derivation is valid here because we can use laminar flow. If the same Reynolds number 22, Reynolds number 1500 here, so there is a waves grows rapidly, it is like moving from laminar flow to turbulent flow in between that one. So, here again the assumption is Vz is a velocity is a function of only x, the steady state flow, then no longer this one. Our earlier assumption also with little bit valid approximately. So, in the case the turbulent flow, what will happen? Turbulent flow is a greater than 1500, we called as the turbulent flow here. The flow becomes a irregular, then strongly is a time dependent. So, large amount of due to eddy is also there. So, this here why we want to this indicate this fluid mechanics rely on theory, the main part is the governing equations are nonlinear. Whatever the governing equation we are using, that most of the equations are nonlinear and instabilities arise spontaneously, suddenly it is spontaneously here. So, there is a transition to turbulence cannot predict exactly when it is happening transition to turbulent. So, that part is very difficult, that one. So, definitely we need whenever do modeling, we need a experimental value also, because whenever we do in the this one, we always do the modeling part and we will do little bit experimental part, always we compare with the modeling and experimental results. If both are getting match, then our model and then experimental is matching. If it is not matching, what we have to do, that whatever the modeling, you have to solve it or you make some other assumptions or do some optimization, so that the both results will get a match here. So, this experimental identify flow regime here definitely we need, then only we get a thorough knowledge, that one. Same way for theory is also explained, that one, both are very essential, these are all essential for here. So, small example problems we will see here, the water at 20 degree, the flowing the down vertical, the angle is the beta equal to 30 degree angle here, but the Reynolds number is a 12, the Reynolds number is a 12. The first they are asking calculate the flow rate, but always use the SI units, but here they are using the different unit, but we can use normally we can solve the SI units. Then there is a maximum velocity, of course these all derivation we already discussed, we just use the analytical that last one, then we can just solve that one, nothing here. So, another one is for the film thickness for both cases. So, the Reynolds number 12, the water, then water property density is a 998, the problem already given, the viscosity also it is there, then the gravitational this G is equal to 9.81. For vertical wall, the beta 0 degree, same way for inclined wall beta equal to 30 degree. So, Reynolds number, this is a formula we are going to use here, Reynolds number here already we know that one, the Q is a volumetric flow rate, V max is the maximum velocity, they are asking maximum velocity, the problem is the maximum velocity they are asking, then finally the film thickness they are asking here. So, you have to just substitute the value, get the answer. The Reynolds number here, the Reynolds number, the 4 rho delta by this one, we can write in terms of mass flow rate, the W, because mass flow rate W equal to, we can always write Q into rho. Of course, we know already, we discussed also. So, this is called a mass flow rate, not a volumetric flow rate. The mass flow rate is the kg per second, mass flow rate. So, here the mass flow rate here, the mu, that is viscosity, Reynolds number, then 4. So, after solving this one, we will get a kg per meter per second, because the units viscosity in the same unit will get, because per unit length is here. Okay, they are mentioned the per unit length. So, the mass flow rate here kg per meter per second, this one. So, from there then volumetric flow rate you have to find, volumetric flow rate, we know volumetric flow rate Q equal to W by rho, but the units are here kg per meter second here, then other is the kg per meter cube. After solving we get in terms of meter square per second, but there itself they are asking in for okay, in per meter of wall or whatever, okay, there the flow itself they are already with respect to length they are asking the flow rate per unit length or whatever for flow rate per the length. So, the length is here again you have to make 1 feet equal to 0.3048 meter, then we will get the Q value, the Q is a 9.9 10 power minus 7 meter cube per second. So, in terms of convert to gallon per hour, of course, you can use something, then finally we got this one. So, first one we solved, the next one is for the film thickness here, the B part, you know delta the equation and you just make it to solve delta cube equal to this one, you just substitute all the value, the viscosity value, mass flow rate you know, then W, that is a density square is there. So, all you can substitute, then we will get a delta equal to in terms of meter, but finally they are asking in terms of inches, delta equal to 0.038 inches here. So, that also we can do here. So, for inclined wall delta cube, so now the two wall is there, no? One is for cos 30, the other one is for this one. So, here the delta cube equal to same equation, the beta we used to cos 30 here, the previous problem cos this is 0 vertical wall. So, there is a two problem, one is the vertical wall, then another one is for inclined wall. So, both wall is there, for vertical wall the beta equal to 0, for inclined beta equal to 30 degree. So, the two problems we are simultaneously solving here. So, beta equal to 30. So, the delta equal to 0.04 for inclined wall. Same if for maximum velocity you can confound, we know already the formula, just substitute, then we got a V max here 0.046 meter per second, V max here. So, then inclined wall, what is this one? So, finally, the overall picture, what is the flow rate, what is the velocity in vertical wall, inclined wall, then the thickness, then gravity, we gave as a table form, it is easy to understand. Okay. Thank you.